Welcome to this lecture number 17 on the NPTEL course on fluid mechanics for undergraduate chemical engineering students. In lecture number 16, we started discussing the integral energy balance. So, let me briefly recapitulate what we did before proceeding further. In order to derive the integral energy balance, the underlying fundamental principle is the first law of thermodynamics, which says that the change in total energy of a system is equal to the amount of heat transferred to the system minus the amount of work done by the system. Okay. So, this is heat into the system, this is work by the system. So, this is the sign convention that we use, that the work done by the system on the surroundings is positive, okay, and the work done by the surroundings on the system is negative. Okay. That is a sign convention that is normally used in engineering thermodynamics. Okay. So, we also pointed out that in engineering applications you will always have continuously flowing systems. So, it is good to rewrite the first law of thermodynamics in a rate form, which says that the rate at which the energy of a system changes, okay, is equal to the rate of heat transfer to the system minus rate at which work is done by the system on the surroundings. So, Q dot means it is the rate at which heat is transferred to the system, and W dot is the rate at which work is done by the system on the surroundings. Now, in order to convert this to a control volume kind of an approach, control volume kind of a formulation, this gives, we have to use the Reynolds transport theorem as usual, which will give, and before we do that, we realize that the energy of the system is equal to the volume of the system of the specific energy times, which is energy per unit mass, times density, which is mass per unit volume, integrated over the volume of the system. So, we want d dt of this, so which is d dt of this. In order to do this, we have to use the Reynolds transport theorem, which will tell us that this is nothing but the rate of change of energy of the control volume. Okay. Remember that when we use the Reynolds transport theorem, okay, we always imagine that you have a CV at some time t naught, the system and CV coincide. Okay. The system and the CV are exactly the same at time t naught, but CV is fixed in space, it is independent of time, but the system, which I am marking in red and blue, at a later time, blue is at a later time t naught plus delta t, the system would have moved out of the CV by virtue of flow, and the rate of change that we are talking about of the system is that at that particular instant of t naught, what is the rate of change of energy of the system, okay, and that is given by Reynolds transport theorem in terms of the variables pertaining to the control volume as follows: rho e dV plus integral over the control surface rho e v dot n ds or dA. If you had used dA, let us keep using dA, is equal to q dot minus w dot. Okay. In order to understand various contributions to the work interactions between the control volume and the surroundings, we imagined in the last lecture drawing a general kind of an engineering equipment, which is typical in many fluid mechanics applications, okay, where you had a shaft, okay, and this shaft has a rotor, which could be an impeller, which is rotating at some angular velocity, and the system, the control volume is the blue line, okay, and we want to write the balance about this control volume, and you want to understand what are the work interactions. Okay. Now, there are three types of areas, as we said in the last lecture. The internal areas AI, where there is the velocity of the fluid is 0, okay, then these areas through which flow is happening AF at the inlet and outlet, and this area over which the control surface is cutting across the rotating shafts that can protrude out of the CV to the surroundings. Okay. So, there are 3 types of areas, okay, and the work interactions, as we said last lecture, work is simply force dotted with displacement, the rate at which work is done by this. So, first we discussed the rate at which work is done by the CV on the system, and then we took a negative sign. So, rate at which work is done is delta W by delta T. So, ds by dt is the velocity. So, rate at which work is done is F dot V. Okay. Now, all we know in fluid mechanics is the stress vector. Okay. So, W dot is integral of the stress is force per unit area, as we have been mentioning, over the entire control surface area. Okay. Now, the entire control surface area has 3 type of areas. One is AI, AF and A shaft. Okay. So, we have to split this integral into these 3 areas. Now, before we do that, we also said that the total stress vector can be written as a normal component plus the tangential component. Okay. So, this is work done by the CV on the system. So, let me just put it as WCV, sorry, work by the surroundings on the CV. So, let us just write this as delta W surroundings. When we want the work done by the CV on the surroundings, we will take the negative signs. So, let me just do this right now. So, rate at which work is done by the surroundings on the CV is nothing but integral sigma n over all the control surfaces plus sigma t dot V dA, okay, integrated over all the area. Okay. So, let us split the normal and tangential components separately, integrated as integral over Cs sigma n dot V, okay, dA plus integral over Cs sigma t dot V integrated over dA. Okay. Now, sigma n, okay, is okay. Now, let us now split this further, sigma n dot V dA plus, now let us split this surface area into a control surface area into control surface over A internal areas dA plus control surface over flow areas dA plus control surface over shaft areas dA. Now, if you look at the internal areas, the velocity at solid surfaces of the control surface is 0. So, this contribution is 0. If you look at the control surfaces over the flow areas, okay, this can be, see this is, let us say, the flow, okay, this is the direction of velocity. If you choose the control surface perpendicular to the unit normal to the control surface perpendicular to the flow direction, then the tangential stresses will act in the direction perpendicular to the velocity. So, these 2 vectors are orthogonal. So, this can be set to 0 if n is perpendicular to V. Okay. If the unit, sorry, if the unit, if V is perpendicular to the control surface, that is if n is parallel to V, that means that the velocity vector and the shear stress vector are orthogonal to each other. So, that is 0. Now, this contribution is not 0 because whenever there is a rotating element, okay, and the Cs is cutting across it, there is a stress and then there is also a velocity in the direction of stress. So, this is the shaft work, which is denoted as W dot shaft, rate at which shaft work is done. Okay. So, rate at which shaft work is done by the surroundings on the CV. So, we are still looking at the rate at which work is done by the surroundings on the CV. So, this is integral over Cs sigma n dot V dA plus W shaft. Now, rate at which, but the quantity that we are interested in is rate at which work is done by CV on the surroundings. It is minus integral Cs sigma n dot V dA plus or minus, because it is negative of the previous expression, W shaft. Okay. Therefore, the integral energy balance becomes d dt of integral rho e dV, integral over control volume, plus integral over control surface rho e n dot V dA is equal to minus integral sigma n dot V dA minus W shaft plus Q dot. Okay. So, this is the simplification that we get after we use the fact that the shear stresses, the rate at which work is done by the shear stresses are 0 on the internal areas, and as well as the fact that the shear stresses cannot do work at the inlet and exit as long as you choose the control surface such that it is perpendicular to the inlet velocity vector. So, that the velocity vector and shear stress vector are perpendicular to each other. Okay. So, finally, we get, but you also know that sigma n is minus p. Okay. So, if you remember our very first discussion on hydrostatics, if n is pointing outwards, okay, then pressure is pointing in the direction of minus n. Okay. So, this is the normal component of the stress, but pressure is acting in the direction of minus n. So, sigma n is minus p. So, but there are also, we pointed out in the last lecture that there are also normal viscous stresses which are usually negligible, okay, in liquids like air and fluids like air and water. So, we get the following expression d dt of integral rho e dV Cv plus integral rho e n dot V dA Cs is equal to minus W dot shaft plus Q plus integral P n dot V dA. Okay. Now, we can pull this, both these expressions have n dot V times dA. So, we can pull this to the other side to write rho e dV Cv, okay, integrated over Cv plus integral over Cs rho times E plus P by rho n dot V dA is minus W shaft plus Q dot. Okay. So, this is our final simplified energy balance. We will further simplify it by assuming, now we will assume certain things, that is, it is uniform flow. First, we will assume steady flow, uniform flow, where the properties are uniform across the inlets and outlets of the control surface. Okay, so that the integrals can be simplified. We will of course relax this assumption a little later, and so we will try to simplify this energy equation for the special case of uniform and steady flows, wherein you will get summation. And when we do this, we should also realize that n dot V is minus V at inlets and n dot V is plus V at outlets. So, the integral over the Cs will become a summation over outlet rho E plus P by rho times V dA is summation over inlets rho E plus P by rho, not V dA, just VA minus W shaft plus Q dot. Okay. So, you remember that the specific energy, specific total energy per unit mass is the internal energy plus per unit mass plus the potential kinetic energy per unit mass plus kinetic energy per the kinetic energy per unit mass plus potential energy per unit mass. So, E is U plus half V squared plus GZ. Okay. That is something that we should keep at the back of our mind. So, we will write summation over outlets, okay, U plus half V squared plus P by rho plus GZ times rho at outlet at rho VA at outlet is summation over inlet U plus half V squared plus P by rho plus GZ at inlets rho VA minus W dot shaft plus Q. Now, rho VA for a steady flow at the inlet should be equal to rho VA at outlets. This is mass conservation. Okay. If there is only one inlet and one outlet, okay, then you know that rho VA at inlet is rho VA at outlet minus m dot. So, we can divide the entire, which is the mass flow rate, divide the entire equation by above equation by the mass flow rate to give U plus half V squared plus P by rho plus GZ at outlets. So, let us just specialize to the case of single inlet and single outlet. Out is U plus half V squared plus P by rho plus GZ in minus W dot shaft plus Q dot. Okay. Now, this is the most general energy balance. This is the special form for energy balance for a steady flow, uniform flow, and also with single inlets and outlets. If we restrict ourselves to incompressible fluids are fluids where, as we have said some time back, rho is constant, that is, it is independent of pressure. The pressure changes that are associated with the fluid flow does not change the density of the fluid flow, then the fluid is said to be incompressible. In such a case, the pressure P is purely a mechanical variable, it is not a thermodynamic variable. So, people normally write take in U, whereas U, the internal energy is a thermodynamic variable. So, you take U to the other side to write this as P by rho plus half V squared plus GZ at outlet is P by rho plus half V squared plus GZ at inlet minus W dot shaft, okay, minus U out. Okay, so, we are trying to divide the entire equation by W dot. So, you will get W dot shaft by m dot, Q dot by m dot. Okay. Now, W dot shaft by m dot is nothing but small w, it is the work done by the CV per unit mass of the fluid. There is no rate because you are dividing one rate with another. This is the rate at which work is done by the CV on the surroundings. This is the rate of mass flow. The two rates will cancel out to give the rate at which work is done by the CV on the surroundings per unit mass of the fluid, and you will get minus U out minus U in, okay, minus Q, sorry, because you have already taken a minus sign out. Small q is the rate at which heat is transferred to the fluid per unit mass. There is no there is no rate, the heat transferred to fluid per unit mass. There is no rate involved with here. Okay. So, finally, we have a simplified equation for steady flow, uniform flow, that is the flow properties such as velocity, density, internal energy, they are invariant with the cross section at inlets and outlets. Steady flow, uniform flow, single inlet, single outlet. And finally, we also have incompressible flows. Okay. The simplified energy balance, integral energy balance becomes simply, so let us start with P by rho, that is conventional, V squared by 2 plus G z let me again start with P by rho here also, P by rho plus V squared by 2 plus G z minus W s, the rate at which shaft work is done by, the amount of shaft work done by the fluid per unit by the CV per unit mass of the fluid, minus U out minus U in minus Q. Okay. So, what we are saying essentially is that for an incompressible fluid, okay, the heat transferred, okay, can affect only the internal energy. For example, the heat that you are putting in cannot go into increasing any of these, that is why these two terms are clubbed together. Okay. But suppose for the moment, let us say that the CV is adiabatic, that is when the CV is adiabatic, Q is 0, no heat transfer to or from the fluid. Okay. So, you get P by rho plus half V squared plus G z at outlet is P by rho plus half V squared plus G z at inlet minus W s minus U out minus U in. Now, there is no heat transfer. Now, the question that we can ask is, will this term be 0 or non-zero if there is no heat transfer whenever there is a fluid flow. Okay. So, it turns out that whenever there is a fluid flow happening within pipes or in equipment like pumps or compressors, okay, there is always an irreversible transfer or conversion of macroscopic mechanical energy to internal energy. Okay. So, this is a fact that whenever there is a fluid flow, the viscous action of the flow of the fluid, okay, the viscous nature of the fluid always dissipates energy from macroscopic motions to microscopic degrees of freedom, which is essentially the internal energy of the fluid. Okay. So, U naught minus U I is always greater than or equal to 0. The equality happens when you consider a fluid with 0 viscosity. Of course, there is no real fluid with 0 viscosity, but if you consider a hypothetical or ideal fluid that has 0 viscosity, then you will have no conversion of mechanical energy to internal energy. This is called the viscous dissipation of energy. Okay. So, this term will always be greater than or equal to 0. Okay. Now, in the context of fluid flows, okay, this is the energy that is lost. So, these are termed as losses, viscous losses, because the macroscopic energy that you have supplied by way of kinetic energy or gravitational potential or the pressure, okay, has been lost to internal energy. So, these are termed simply as viscous losses. So, in engineering fluid mechanics, we will simply for incompressible flows, okay, with all the assumptions of steady uniform flow, one inlet, one outlet and incompressible fluids, the energy equation is normally written as plus G z at inlet minus W s. This is the shaft work done per unit mass of the fluid by the CV on the surroundings minus W loss. This is the amount of energy lost to internal energy by the viscous dissipation action. Okay. So, this is a new, we have to tell what the losses are, okay, in order to solve a problem, but we certainly know that there are losses. Okay. How these losses are computed for simple systems, we will come to a little later when we do differential balances of momentum. Okay. But right now we know for sure that losses are there. Okay. Whenever there is a fluid flow, there will be loss of energy from macroscopic form, be it pressure head or kinetic energy head or the viscous law or the gravitational potential energy in any form. to the internal degrees of freedom, which is the internal energy. But if you are looking everything from a macroscopic point of view, that is the energy that is lost from the macroscopic side. So, we just term it as viscous losses. Okay. So, normally then therefore, we write the internal energy balance like this. Sometimes in engineering fluid mechanics, you divide this entire by g acceleration due to gravity to get p by rho g plus v squared by 2 g plus z at outlet is p by rho g plus v squared by 2 g plus z at inlet minus w s by g minus w l by g. Now, if you look at this equation, each term has dimensions of length. So, historically or traditionally, people worried everything, people thought about various energies in terms of pressure heads. So, this is the gravitational head. So, this is called the gravitational head because it has dimensions of length. This is a head called gravitational head. This is the kinetic energy head. This is the pressure head. Now, W s by g is denoted as H s, W l by g is denoted as H l. Okay. There is no new information in this equation, except that in many a times you will see textbooks discuss this form of energy balance also, where every quantity is represented in dimensions of length, which essentially represents a height of a column of liquid in the gravitational potential energy sense. So, that is why all these terms are defined in the form of heads. Okay. Now, that is the simplest form of energy balance. As we told in the last lecture, that if for non-uniform flows, that is where the velocities are a function of the cross sectional area, okay, then it is just as we introduced the momentum correction factor in the last lecture. For the flux terms in the energy balance, you may have to carry out this integral. So, you have half. So, if you recall, you have a term of the type rho half v squared v dot n dA over the control surface. Okay. So, this is essentially, if you are considering about, if you are thinking about outlet, v dot n is positive. So, if you are considering about inlet, v dot n will be negative v, but essentially you will have to evaluate an integral of the form half v cube dA, where v is a function of the cross sectional area. Okay. Now, you want to be able to write this in the form of a new correction factor alpha times half v average cubed, okay, times rho V A is m dot. So, let us write this as times rho A. Okay. So, we will just write rho A. We want to be able to write, instead of doing this integral, we want to write this integral as though if it is a uniform flow, then the answer will be half V cubed times rho A, but now we substitute V by V average because the flow is non-uniform. But you also introduce a correction factor. This is called the kinetic energy correction factor. So, in order to find what this kinetic energy correction factor is, we have to simply, so alpha is equal to 1 over area u by V average whole cubed dA. Okay. So, if you use, so if V for a pipe, for pipe flow, laminar pipe flow, okay, laminar. So, V of r is some maximum velocity times 1 minus r squared by r squared. So, we can calculate what is V average and then we can calculate alpha. So, for laminar flow in a pipe, alpha becomes 2, whereas for turbulent flow in a pipe, alpha is simply 1.04. Okay. So, you could for non-uniform flows use the correction factor, kinetic energy correction factor. So, for the simplest case, special case of steady flow, uniform flow, incompressible fluid, and then single inlet, single outlet, you get P by rho g plus alpha V squared by 2 g plus Z at inlet is P by rho g plus alpha V squared by 2 g plus Z at outlet plus the head due to shaft work plus H due to losses, viscous losses, the head due to losses. So, this is the most this is a special case where you assume steady flow, uniform flow, incompressible fluid and single inlet, single outlet, but sorry, we are not considering uniform anymore, because you are removing the uniform flow assumption by introducing the kinetic energy correction factor. If the flow is uniform, alpha is 1. If the flow is laminar, alpha is 2. If the flow is laminar, alpha is 2 and alpha is 1.04 if the flow is turbulent. So, this is very close to 1. That is because of the fact that the turbulent flow velocity profile is in fact uniform, very close to being uniform. Therefore, it makes sense for us to approximate alpha to 1 for turbulent flows. Okay. So, that completes the basic discussion on energy balance. Now, I want to point out an important distinction between this energy equation, which we derived from first law of thermodynamics, to another equation which many of us will be familiar with, that is the Bernoulli equation. Okay. If you look at the Bernoulli equation, if you are already familiar with the Bernoulli equation, it may appear very similar to the energy equation. Okay. But let me try to derive the Bernoulli equation from the energy equation that we just derived. Okay. So, in general, if you have a fluid, okay, the fluid velocity, we define what are called streamlines. Streamlines are always parallel to the local velocity vector. Okay. So, in a fluid flow, in a steady fluid flow, you can describe the flow pattern using a bunch of streamlines by plotting the streamlines. If you collect a set of streamlines, you can form what is called a stream tube. It is a bunch of streamlines that are collected together. It is like a tube. Okay. So, the stream tube, the surface of the stream tube itself are comprised of streamlines. Okay. A basic definition of streamline is that fluid velocity is tangential to the streamline and there is no flow normal to the streamline. So, therefore, the stream tube is almost like a tube of a complicated shape, but it is still a tube, okay, in the sense that there is no flow, net flow out of the stream tube in the normal direction. Fluid can come in and flow, but there is no flow in this direction, because by definition the streamlines are parallel to the flow velocity vector. Okay. But this is not like a rigid container, rigid conduit, because the stream tube is surrounded by fluid and in general the fluid can exert stresses, viscous shear stresses. Okay. So, I want to apply the energy balance to this control volume where you have a stream tube. The stream tube is our control volume. Okay. Now, we will make some major assumptions in order to derive the Bernoulli equation, that these will tell us the crucial distinctions between the Bernoulli equation that we are going to derive and the most general form of energy balance, which is a statement of first law of thermodynamics. Okay. We will assume that fluid is incompressible, rho is constant, Okay. Second, we will assume that there is no heat transfer. Okay, from the outside to inside or vice versa, and there is no shaft work within the stream tube. Okay, no shaft work. We are just considering plain flow. There is no reason for us to expect that there is a shaft work present. Okay, no shaft work. So, these are the three major assumptions. Once we do this, okay, and further assume a most important assumption, that the fluid is non-viscous or inviscid. We are considering the fluid is a hypothetical fluid with 0 viscosity. Okay. Once you do this, we can simplify the energy balance to the Bernoulli equation. So, by making these specific assumptions that flow is incompressible and there is no heat transfer, there is no shaft work, and most importantly that the fluid is non-viscous, inviscid, there is no viscosity. Okay. And we apply the energy equation to this specific control volume called a stream tube. A stream tube is essentially a bunch of streamlines that are present in a flow, and we collect a bunch of streamlines and encircle them. Okay. And the stream tube itself, the surface of the stream tube itself is comprised of streamlines. So, there is no flow in or out of the stream tube to the sides. So, it can only come in and go out through the entry and exit. There is no flow in through, there is no normal flow through the sides of the stream tube. Okay. By definition, the fluid velocity is parallel to the surface, it cannot go perpendicular. Okay. If you assume all these things, then the most general form of the energy balance which we wrote with single inlet and single outlet for incompressible fluids is the following: V squared by 2, okay, plus G Z V squared by 2 G plus P by rho G. So, let me write P by rho G first as usual, P by rho G plus V squared by 2 G alpha plus Z at in is P by rho G plus alpha V squared by 2 G plus Z out plus H shaft plus H friction. This is the most general equation. Now, we are going to simplify this. We are saying that there is no shaft work, 0, and there is no viscous shear stresses at the sides, because we are assuming the fluid to be inviscid or non-viscous. So, there are no viscous stresses, the work done by viscous stresses on the CV, on the control surfaces of the CV. So, that is 0. There is no viscous loss because the fluid is inviscid. So, this is a very critical assumption, and we will assume uniform flow. So, alpha is set to 1, that is further an assumption. So, if you do all this, you will get a simple equation. Okay. Now, P by rho G plus V squared by 2 G plus Z at inlet is P by rho G plus V squared by 2 G plus Z at outlet. Okay. Now, this we can further simplify the stream tube or further shrink the stream tube to an infinitesimal thickness. In the limit, it becomes a streamline. So, this equation, which is called the Bernoulli equation, the classical Bernoulli equation, is applicable to an inviscid fluid, okay, 0 viscosity, okay, to a streamline. It is applicable only between 2 points along a streamline, along the same streamline. Okay. Of course, we have made further assumptions such as steady incompressible flow, which are more which are less restricted assumptions. But the critical assumption for the application of Bernoulli equation is an inviscid fluid and a streamline. Okay. Whereas, the energy balance that we wrote, okay, is generally applicable to any control volume, okay, and as long as you can supply the problem or with the information about what are the viscous losses, you can completely solve it. Okay. And it is applicable to any flow of viscous liquid into any equipment like a pump or a piping network and so on. As long as we know what are the losses, we can certainly solve that most general energy balance equation, integral energy balance equation. Okay. But this one is more restrictive, the Bernoulli equation, although it appears very closely similar to the integral energy balance. It is not, because it is applicable only to an inviscid fluid, of course assuming steady and incompressible flow, and further it is applicable only along 2 points along a given streamline. Okay. That is the very strict limitation on the application of the Bernoulli equation, whereas the integral energy balance equation is always valid for any complex flow process that you may encounter, which may have pumps and compressors. So, you can take into account what is the shaft work contribution and so on very easily, but you need to know what are the losses involved in a given situation. Okay. So, that is a major major input to the problem before we can solve a problem. Okay. So, we can ask the question, when can the Bernoulli equation when can the Bernoulli equation be valid? So, suppose you have a system like this, you have a flow past an airplane model, you have a tiny airplane, okay, this is a model airplane, and you have flow, let us say the airplane is stationary and flow is coming like this, okay, very close to the solid surfaces. We will see later that viscous effects will become important. This is called a boundary layer. So, here wherever I am patching with blue, Bernoulli equation is not valid. Okay. So, very close to the airplane surface as well. Okay. There will be viscous effects that are very important. So, the Bernoulli equation will be invalid in the blue patches, but if you take a streamline where there is no blue patch, then you can certainly apply the Bernoulli equation between these 2 points, because you can assume that there is, to a good approximation, that viscous losses are negligible. They are never 0, but they are not that important. Okay. Likewise, let us consider another context. Okay. You may have a conduit like this, okay, and you may have a fan or a blower, okay, and fluid is coming in like this and going out like this. Okay. So, close to these solid surfaces, okay, close to these solid surfaces, viscous losses will be important. Okay. So, you can apply Bernoulli equation in the upstream and downstream of this blower or a fan, okay, along a streamline, but you cannot take the streamline across this fan, because viscous losses become important. So, the Bernoulli equation is valid. Okay. So, P by rho plus half V squared, P by rho g plus V squared by 2 g plus Z is a constant along this streamline. It is also a constant along this streamline in the downstream, but the constants will be different because of the fact that you have an equipment like a shaft or a fan which is trying to do work on the fluid and so on. So, clearly the Bernoulli equation is not valid in this region. So, the Bernoulli equation is a very simple equation, and it can be used in many contexts to get a first cut result, but in certain contexts obviously the Bernoulli equation is not valid. Okay. And you should know when to apply the classical Bernoulli equation and when to apply the integral energy balance. The integral energy balance is certainly more general, in that it accounts for viscous losses and it also accounts for shaft work contributions either in or out of the CV. Okay. But whereas the Bernoulli equation of course cannot take into account all these complications. Okay. Now, this is really what I want to say about the energy balance, okay, integral energy balance. Now, we have to apply this integral energy balance to some specific context. Okay. Now, the context which I am going to discuss first is flow measurement. Okay. So, the question that we are going to ask is, in an industrial setting where you have complex networks of pipelines that are going here and there, how can you measure the flow inline? Okay. One obvious way to measure a flow is, of course, if at the exit of the pipe you collect the water, okay, and you measure the volume of the water for a given amount of time, and that gives you a sense of what is the volumetric flow rate that is happening in the process in the network of pipes. But if you want to do something inline, that is without having to wait for the exit of the flow, somewhat in between the network itself, if you want to know what is the flow rate, which is very important in many chemical engineering applications, how do you do that? Okay. So we want to do something within the pipeline network. So we have a set of devices called restriction flow meters. Okay, for internal flows, that is, you have flow in conduits such as pipes or channels, okay, and you want to know the flow rate that is happening inside those pipes and channels. So these flow meters look something like this. This is a general schematic where there are, of course, specific details which we will come to a little later. The general schematic is as follows. This is the pipeline, okay, and the flow meter reduces the cross section of the flow and suddenly expands it, and of course the pipeline diameter is the same upstream and downstream. Okay. So this is the general schematic. Okay. Now far away the fluid is flowing with some average velocity V1, and the diameter of this tube is D1. Okay. Now we want to know what is the velocity, given that we know what is the diameter. Okay. In order to do this, we have to draw a CV. The CV is the green line, okay, that I am going to draw. It adjoins the cross section of the flow meter, okay, very closely. This is my CV. Okay. So fluid is coming into the CV at station 1, and it is leaving the CV, okay, at some other station. Now that is the CV that we are going to work with. Okay. Now if you look at the nature of the flow, the fluid will come like this, okay, and it will go like this, okay, and there will be recirculating zones, okay, of fluid. Okay. These zones do not contribute to any flow rate, okay, and we are going to, let us draw the CV like this. We are going to draw the CV where, okay, this is our CV. Let me draw the CV again. This is our CV. Okay. So fluid is coming in like this, okay, far away it is uniform, and it is restricted deliberately by the flow meter. So here the velocity will increase, and because there is a sudden expansion, there will be some recirculating zones of fluid like this in the upstream, in the downstream of the contraction, okay, and the fluid eventually leaves. Okay. So the idea is to measure, in order to find what is the velocity, we have to measure the pressure drop between the stations 1 and 2, okay, and using that we want to infer the average velocity upstream of the flow meter. So that is the idea. By measuring the pressure difference or pressure drop that happens between the upstream and downstream sections of the contraction of the flow meter, by measuring the pressure drop, we want to be able to relate that to the velocity. Okay. So what are the basic principles that we have? We have mass conservation, okay, mass balance, integral mass balance, and energy balance. Okay. So the mass balance, so let us first write, let us also make some assumptions, because this is a fairly complex problem, it cannot be solved without making these assumptions. First is steady incompressible flow and we want to consider the flow along a streamline from points 1 and 2. Okay. We will assume no friction and uniform velocities at stations 1 and 2. So, essentially we are considering a streamline and we want to write we will use the Bernoulli equation and correct it later, because we are assuming no friction, no viscous losses. No frictions means no viscous losses. Okay. So, but that is not a good assumption, we will correct it later, and we will also assume that the elevation is the same between points 1 and 2, that is a good assumption. So, if you use the Bernoulli equation, P1 by rho plus V1 squared by 2 plus Z1 is P2 by rho plus V2 squared by 2 plus G Z2. Z1 is approximately equal to Z2. Okay. So, that is there. So, P1 minus P2 becomes rho by 2 V2 squared minus V1 squared. Okay. Now, if you use the continuity equation, the mass balance equation, rho 1 V1 A1, rho V1 A1 is rho V2 A2. Since the fluid is incompressible, density is constant, so you can cancel it out. So, V1 by V2 is simply A2 by A1. Okay. We will stop here and we will complete the discussion in next lecture. So, on this discussion on application of energy balance to the case of flow measurement. Okay. These are called flow meters. So, we will stop here now and thank you for your attention.